Hello and welcome to Controllers H. I have decided to continue the videos on STM32 Dual Core MCUs, and for another couple of weeks, I will release videos on inter-core communication using different means available. I have already made a video on how to get started with the Dual Core MCU, where I covered how to program the MCU, and how to debug it. Today we will start with the hardware semaphores, also known as HSEM. As their name suggests, HSEM is just like the binary semaphores we covered in the RTOS, but these are built on the hardware level. They are not used for the data transfer, but rather used for notification, synchronization, and for the shared resources. Today we will see how to use the hardware semaphore for the inter-core notification, for the core synchronization, and how to use it to block the shared resource. Let's take a look at the reference manual of STM32H7. Here we have the topic hardware semaphore. This block provides 32 register-based semaphores, along with a non-blocking mechanism to lock to semaphores. There are two ways to lock a semaphore. In a two-step lock, we need to write the core ID, and the process ID, followed by a read check. And in a one-step lock, we read the core ID from the semaphore. We will be using the whole functions to lock and release the semaphores, so it will be a bit easier for us. Each semaphore can generate an interrupt, and semaphores are released only when core ID and process ID matches with which it was locked. So there are 32 semaphores in total. The process ID can be 8-bit in size, and the core ID can be 4-bit. You can read more about the semaphores, but we don't need too much info for today's tutorial, so I will skip this. Let's start the CubeIDE, and create a new project. I am using the STM32H745 Discovery Board. Give some name to the project, and click Finish. Let me clear the pinouts first. I have already covered the clock setup in the Getting Started video, and I am following the same here. The system is clocked by the external 25 MHz crystal, and is running at 400 MHz for the M7 core, and 200 MHz for the M4 core. There are two LEDs on board, and I will use them to demonstrate the inter-core communication. LEDs are connected to the pins PI13 and PJ2, so I am setting them as output. Now we need to assign these pins to individual cores. I am assigning I13 to the M7 core, and J2 to the M4 core. These pins are inverted, so we will pull them high initially, so that the LEDs will be off by default. We also need to enable the interrupt for the semaphore. The NVIC1 is for the M7 core, and 2 for the M4 core. I am enabling the interrupt for the HSM2 in the M4 core. That's it for the CubeMX, click Save to generate the code. Here we have the two main files for the CM7 and CM4. Let's build them both before proceeding further. We will start with the core notification first. Here the M7 core will send notification to the M4 core. The M7 will first take the semaphore with the ID 0. This is already defined by default, as the pre-generated code also uses this semaphore number 0. After acquiring the semaphore, we will toggle the LED 10 times, with a delay of 250 milliseconds. Then the semaphore will be released. The fast take function is used to take the semaphore without mentioning the process ID. When we use this function, the process ID is automatically assumed to be 0. When using the release function, the process ID must be mentioned, and that's why it is set to 0. Now in the M4 core, we will use the notification sent by the M7 core. Let's create a variable, and assign it the value 0. If the notif received is 1, means the notification has been received. We will simply toggle a LED here. We need to activate the HSEM notification in the main function. We have activated the notification for the HSEM 0, so when the M7 core will release the semaphore, an interrupt will trigger, and the HSEM free callback will be called. Inside the callback, we will set the variable notif received to 1, and activate the notification again. Let's understand it one more time. The notif received is set to 0, so the code can't run in the beginning. The M7 core will toggle the LED 10 times, and then release the semaphore. This will trigger the interrupt in the M4 core, the notif received variable will be set to 1, and the second LED will toggle once. This process will keep running forever. Let's build both the files. Now we will create the debug configuration, so make sure you are in the M7 main file. Now click on the Run configuration, and double-click here. The configuration should be generated for the M7 core. Go to the Debug tab, and check Halt All Cores. Now go to the Startup tab, and click the Add button. From the drop-down menu, select the CM4 option, make sure everything is checked here, then click OK. Now we need to move the CM7 configuration to the top here. Everything is done, click Apply, and run the configuration. This will load the code to both the cores, but we need to manually reset the board after the loading has been finished. Here the red LED is controlled by the M7 core, and the green is controlled by the M4 core. The red LED is blinking 5 times, and then the green LED toggles once. Basically the M7 core is toggling the red LED 10 times, then it is sending the notification to the M4 core, and finally the M4 core toggles the green LED once. So we were able to make one core send the notification to the second core using the hardware semaphores. Next we will see how to synchronize both the cores. In this case the M7 core will first run and finish its job, then the M4 core will start doing its job. In this way the cores will be synchronized where the M4 core cannot run until the M7 has finished working. Here we will first write the code for the M7. Let me toggle this part, and before uploading the final code, I will comment on it properly. The M7 will toggle the LED 10 times. Then it will take the semaphore, and release it. Now let's go to the M4 main file. Here we will wait for the semaphore to be taken. This function will return 1, once the semaphore is taken. The control will wait at this line until it happens, and once it does return 1, we will turn the LED on for 2 seconds, and then turn it off. Let's do the same thing for the M7 core also, it will turn the LED on for 2 seconds, and then turn it off. Then it will take the semaphore, and this function will return 1. Let's build and flash the code to the board. Here you can see the red LED is on for 2 seconds, and then the green LED is on for another 2 seconds. Basically the M7 core is turning the LED on, in the meantime the M4 is waiting for the semaphore to be taken. When the red LED turns off, the M7 core acquires the semaphore, the M4 core can now proceed with turning the green LED on. So the M4 core starts its job only after the M7 core has finished its. We were able to synchronize the cores to do their job sequentially. Now we will see how to block the shared resource using the hardware semaphore. We have covered something similar as the binary semaphore in the RTOS tutorial, where the semaphore must be taken before using the resource, and this is exactly what we will do here also. This time I am using the function HSEM take, and it takes two parameters. The semaphore ID is still the same, and I am using the process ID 12. This is just a random process ID I have used. This statement will wait until the semaphore is acquired, and once it does, we will toggle the LED 20 times, with a delay of 100 milliseconds. Now the semaphore will be released, but make sure you use the same ID that you have used while locking the semaphore. We will use the same code in the M4 core, but with a small difference of blinking time, just to differentiate between which core is blinking the LED. The shared resource in this case is going to be the LED connected to the pin PI13, which is currently defined in the M7 file. We will define it in the M4 file also. Let's build and flash this code to our board. Here you can see the LED is blinking fast 10 times, and then it's blinking slowly. Basically, when the M7 core acquires the semaphore, it blinks the LED at a faster rate, and when the M4 core acquires it, it blinks the LED at a slower rate. So the shared resource, that is the LED, is accessible by both the cores, and they need to acquire the semaphore before accessing it. So we saw how we can use the hardware semaphore to send the notification between the cores, how to synchronize the cores, and how to use the shared resource between the cores. This is it for the video. I hope you understood it. I will continue this series, and more videos about inter-core communication will come in the next few weeks. We will see how to share the memory region between the cores, how to use the Resource Manager utility to transfer data, etc. The link to download the code is in the description of this video. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.